Hi! In today's video, let's take a look at these Miniware's DT71 Smart Digital Tweezers. Banggood sent in this one for me to take a look. And you can check it out on Banggood's website using the link provided in the video description below if you are interested in getting one after watching this video. Now, speaking of Miniware, most people probably are already familiar with its TS series soldering iron. Now, I happen to have one of these TS100 and have been using it for a couple of years now, and I'm very happy with its performance and elegance. So hopefully the DT71 will not disappoint either. I actually have not owned any SMD tweezers before, mainly because of their costs. Although you could get some cheap digital tweezers for around $20, but those typically are limited to resistance, capacitance, and diode measurements only, and they usually do not include inductance measurement capability. For tweezers that do offer inductance testing, the prices are usually north of $200, so I'm glad to see Miniware made an affordable digital SMD tweezer. Even though I say it is affordable, it still costs around $65, while by no means cheap, considering alternatives typically cost at least twice more. So this DT71 is certainly a bargain price-wise in that regard. The DT71 comes in this all-black packaging, which reminded me of the box that the TS100 comes in with, and it does give it a bit of a premium feel. Everything is packed nicely inside this plastic case that the tweezers came in with, and also you get this charging cable, which we'll talk a little bit later, and inside this case you just get your getting started guide and some warranty card. And also you have a spare pair of tips by the look of it that you can replace later. So that's pretty much everything inside this case. And if you want a detailed instruction though, you have to download it yourself as it does not come with detailed instructions. But luckily these tweezers are very easy to use by itself and very intuitive, so you don't necessarily need the user manual itself. And I just printed out a few pages from the user manual, and you can see that we have here essentially what is supported for this digital SMD tweezer. And you can see we have resistance, diode, capacitance, inductance, frequency, voltage measurement. And if you look at the measurement range, is not all that great. But that's something that I mentioned earlier. That's what a lot of these kind of SMD tweezers they offer. And if you look at the second page for the measurement accuracy and parameters, you will see that, again, we have reasonable accuracy. However, the resolution is a little bit on the low side. For instance, in the resistance mode, you can see that if you are above 1 kilo ohm and you're only going to have a resolution of 1 kilo ohm. And also the inductance side, you will see that even in the microhenry range, you get 1 microhenry, and the resolution itself is a little bit limited, but the accuracy itself is actually not all that bad. So now let's talk about some of the design choices that Miniware had made for this DT71. As you can see that it is really a compact package. Now you can see once I pick it up, it started reading, and obviously we can do measurement. So there's some kind of motion sensitive circuitry inside to detect that. And also you can, according to manual, you can just close the tweezers and it will start measuring also. Now for those who do not know, in order to charge this tweezers, you need to unplug the head. You can actually plug in the supplied cable into the tweezer's body itself, and then plug this USB cable into the charger outlet. And so this design is a little bit clunky. I'm wondering why they actually would have separated the head from the body here. And if you recall, we had the TS100. The entire unit is actually in this nice one solid body. Yes, it is a little bit longer and presumably is less ergonomically oriented as the DT71, but in my opinion, the little bit extra length in the unit itself actually is well warranted, especially you don't have to constantly disassemble the unit and charge it and then reassemble it back when you are done charging. So I'm not entirely sure why they have gone this route in designing the DT71. So let me know what you think about this design choice. And the second point I want to make is the placement of the battery itself. And because this whole unit is so tiny, there's really no place for the battery to be placed in the main unit here. Therefore, the batteries are actually placed in the arms of these tweezers. And in fact, it has two, one in each side. If for whatever reason the batteries are dead, you pretty much have to replace the entire unit, as the batteries are not user replaceable. Of course, the battery technology nowadays is mature enough, so I'd fully expect that the included battery would last at least 5 or 6 years, which is reasonable for a gadget of this caliber. And I also wanted to point out is while you're charging this tweezers, you cannot use the tweezer itself. So therefore, if you forget to charge it, the battery is depleted in the morning and you are doing some testing, you will have to wait a little bit of time before you can use it again. So clearly, that's another reason I was wondering why they wouldn't do this integrated design where you can just simply plug in the charging cable and continue using it. So that design choice remains a little bit of a mystery, but that's something I wanted to point out. If you have done firmware upgrade on the TS100 soldering iron before, you will know that the procedure is actually fairly simple, and that's the same procedure used in this TS71 tweezers as well. So basically, you just plug it into the PC, and it will show up as a drive, and you can drop on the latest firmware onto it, and it will update itself. So the procedure is fairly straightforward, and I did that earlier myself. And I changed some of the default parameters, such as the output waveform frequency and the arbitrary waveform itself. So we'll see that a little bit later in the video. Now let's do some measurement. By default, when you power it on, it gets into this resistance measurement mode, and you can change that by tapping the back here, and it's capacitive sensing, so there's no physical button. One thing I forgot to mention earlier is that this tweezer also is designed when you flip it over, the display will flip by itself as well. So that's actually very, very handy if you're left-handed, right-handed, and it accommodates both. And of course, because this is just plugged in, you can rotate the head to the angle that you desire. Now it's a little bit tight, but nevertheless, you can rotate with no problem. And here we have a few resistors on the workbench. Let's just take a look. This is a 10 ohm one, the first one. Let's see if we can accurately measure it. And it's quite tiny here, and you can see that the reading is 9.9. Again, we only have this 1 decimal in this range, but again, the idea here is for you to identify and get the rough idea of the value you're measuring rather than a very accurate measurement. And for that, you can always use another meter here. Although in the spec sheet we saw earlier, the maximum resistance measurement is actually only for 2 mega ohm, but you'll see here I have a 3 mega ohm resistor here. We actually have no problem measuring it. So I'm actually interested to see how far we can push that measurement range. As you see that we have no problem measuring a 3 mega ohm resistor. So for that, I'm just bring in a multimeter and turn into the voltage mode so that we know the voltage input is roughly at 10 mega ohm range. So let's just quickly take a look to see if we can read that. Yep, as you can see, it's 9.8 mega ohm. So it seems that we can at least measure up to 10 mega ohms. So this is actually the first time I'm seeing the spec sheet under-speccing the unit's performance rather than over-speccing it, which is good to know. So now let's move on to the next measurement. We happen to be in voltage, so let's bring a battery. Now this one is going to be limited. It only has a 40 volts maximum measurement range, I think. But nevertheless, it's very useful when you have a coin cell or just some circuitry that is hard to get places and you know that's low voltage. You can definitely use this tweezers to measure. So let's take a look. Yeah, no problem. We're measuring 3.14 volts. And of course, it doesn't have a rectifier inside to automatically detect the polarity. So if you get on the negative side, obviously you are not going to measure anything. So this is actually typical for a lot of tweezers of this price range. But it would be nice that it can automatically detect a polarity. That will be certainly a bonus. So let's move on to the next measurement range. Let's see, resistor, we already did that. And let's do diode. We have a couple diodes here, and let's just see if we can. So this clearly is the wrong side. So let's, yeah, you can see this is a Schottky diode, and we have a 227 millivolts drop. And another one, I think I have another diode here somewhere. This one is a diode. Again, I think it's wrong side. I can't see which is the cathode. Let me just flip it over here. Maybe it's the other way around. And so, yeah. So the contact itself is a little bit of tricky sometimes for these kind of SMDs. And you can see that this is a standard silicon diode at the forward voltage drop of 670 millivolts. And now let's move on to capacitance measuring mode. For that, I have quite a few capacitors here. So let's just change it to, now it went to inductor. Let's go back to capacitor. And let's see here, this random one, I have no idea what that is. So let's, again, the contact is a little bit of tricky. It's a 230 microfarad. And let's get a smaller one, and you can see how fast the measurement really is. So that's actually a very good thing, that when you are measuring these kind of SMDs, sometimes the speed at which you can measure it is more important than the accuracy, as you are just trying to identify the component itself and get a rough idea whether or not the component itself is good or bad. So this one is at 8, well, it's not really cooperating because if the contact is a little bit oxidized, and it's at 8 microfarad. So another one, let's try. This one is 88 nanofarad. So we do have a couple of ones that I do know the approximate range here. So this is a 100 microfarad one. So let's take a look here. And you can see that, yeah, you can see that is 106, no problem at all. And the last one here I have is a, by the look of it, I can't really see it. Let's just take a look at the measurement here. It's 22 microfarad. Okay, yeah, now I do see it has a 22.6 here. That's exactly 22 microfarad. So as you can see that the capacitance measurement mode is also relatively fast and no issues whatsoever. And again, that I just checked the user manual that the capacitance is actually spec'd at maximum of 400 microfarad. And I'm wondering if we can push that limit. And actually, I just did a couple of testing and we can. So that's another surprise I will show you here. So this one, for example, is 820 microfarad. So let's take a look at its measurement here. So you will see that this tweezer has no problem detecting the, now it says it's over, but 840 microfarad. So that's right on the border of what this tweezer can actually measure. So clearly the specs we see are really under-spec'd for both the resistance mode and the capacitance mode for sure. And now let's move on to the inductor measurement. So for that I have a SMD inductor 470. So let's take a look at its actual value here. For that I'm going to switch to inductor. And we're measuring 52.53. So that's a little bit over, but again, these inductors have a very wide range of tolerance. So let's try another one. So this one I'm looking at is a, let's by the look of it, 470. So I would expect the reading to be somewhere around 47. Again, it's 41, 42. And just to show you, the reading is actually pretty accurate. I brought in this LCR meter. So right now we're in the inductance measurement mode. Let me just try to put it here. You can see. So this is the same 470 that we measured before using the tweezer. We're showing about, I think it's 41. Now we're just using this LCR meter to do the measurement. And you will see the result is 44. So it's really not that far off. And when we did the measurement here, let's take another look. Oh, this is resistance. Let's do inductor. Inductance measurement is 41.6. So again, you know, it depends on the frequency that you are measuring it at, and there are other various parameters. Of course, we're expecting slightly different measurement results, but nevertheless, it is largely in the ballpark. And also, according to here, we're only spec'd at 5% plus 3 counts. Next, onto frequency measurement, and for that I'm outputting a 45 MHz signal from my UTG 962E, and that is being measured by these tweezers. Now you will notice that according to the manual, the maximum frequency is actually spec'd at 20 MHz, but now you can see that with a output amplitude of 2 volts peak to peak, we're able to measure up to 45 MHz, and of course if I increase that, 46 you're still able to measure, but obviously 47 is started dropping off. So it does seem that this meter is capable of measuring much higher frequency than is spec'd, and for some reason it just rebooted. So I did notice that once in a while that in certain ranges that presumably the firmware has some issue. It somehow would reboot instead of just powering off. So not entirely sure why. Hopefully in a future firmware update that issue will be resolved. And of course, one of the reasons you get one of these tweezers is to do some kind of in-circuit measurement. So for that, I just brought up the board that is just a random board I have lying around, and we'll try to see if we can do some measurement here. And for that, I'm going to start with this tiny resistor right here. And this is going to be a little bit tricky as it's very, very small. So these tweezers actually, now you look at it, it's not particularly sharp. And for that, I might have some issues measuring those tiny components here. But let's give it a go to see if we have any issues. Yeah, as you can see that we are not able to make a good contact. Now we are, and oh, sorry, you can't see the reading here. So let me move it out so you can see the reading here. And so I have to really press it hard for it to read 280 ohms here, and the same with the other one. So I would have hoped that if the tips are a little bit sharper, like some of the DMM tips, then you would be able to penetrate all these soldering flux on the circuit board, and it would make it much, much easier. But right now you can see that we're struggling a little bit, and also the tips are not very fine, so you can't really easily get into it. But you can see that we can barely clear the other leads here, so it is really tricky here. And let's take a look at the capacitor measurement here. So let's change it to capacitance, and we happen to have a few right here, so let's take a look. And you can see that we're struggling to pick up the capacitance. By the way, I just noticed that when we were doing the capacitance measurement earlier, the readings were actually incorrect. When we're not doing any measurement, you can see that we should be showing zero puff, whereas we're showing overflow. So not entirely sure what went wrong there. But I was switching around ranges, and all the other ranges seem to be working fine except for the capacitance range. So what I had done was unplug this lead and re-plugged it back in, and everything seemed to be working again. So not entirely sure. So now let's take another look at measuring a capacitor in circuit. So let's take a look here. As you can see that it's showing 35 nanofarad, no problem. Now, do keep in mind that in-circuit measurement can be tricky, and not all meters can measure capacitors in all situations. For instance, if I try to measure the other one here, you'll see that this one is not able to measure. Now, that's actually normal. For a lot of meters, it depends on how the arrangement of the capacitors and its surrounding components, you may or may not, to measure the component correctly. And also, I just want to quickly demonstrate the in-circuit LED measurement. And for that, I have this board that has 4 LEDs. So let me change it to diode mode. We can take a look at that. You can see that when the polarity is correct, so if I change it to the wrong polarity, it does not light up. But when the polarity is correct, we'll see that the LEDs are not only lighting up, but also we can read the forward voltage drop in this case. So that's for the green LED. That's for the red LED. You can see that we have the measurement, no problem. Now, one thing I noticed earlier is not only the diode measurement mode, you can also measure the LED and at least light it up in other mode as well. For example, right now we're in the capacitance measure mode. You can see that the LED is also flashing here. So that is just something you need to be aware. And also, for instance, right now we're at the resistance measurement mode. You can also see that the LEDs are lit up. And so far we have been using this tweezers using its manual mode, and we can also use it automatically identify mode, so we can quickly demonstrate here. So for that, I'm going to press this, long press, and you will see that it tries to automatically identify what is being measured. So for instance, right now I have this inductor here, and let's take a look, and you will see that it shows as 11.8 microhenry, no problem at all. Now, once in a while, you will see that it tries to identify a secondary function. So for that, for instance, I have this another inductor, and I think there's some threshold as to what the actual resistance of the coil is, I believe. So now if I can, well, actually if I can get it to measure at all, yeah, you can see that we do see this secondary display, 0.2 ohm here at 108 microhenry. So I believe this is some kind of smartness built in, that when it detects something has a significant resistance and also inductance, it will try to display both. So that certainly comes in handy at times. But I don't know at what point that shows clearly. You cannot see that with this inductor measurement. So presumably the resistance is not high enough. And also we can, for instance, right now we're using this diode, and if you are measuring the correct polarity, you should see the voltage drop and it identifies as a diode. And if you measure the other way around, you will see that it measures, well, if it reads, and sometimes it can, yeah, you can see that it measures as a capacitor. That makes sense, it's a junction capacitance, and also we are touching this ESD mat, so that we do have some resistance. Also, it is being picked up here. I thought that was interesting, just want to point out. And one last thing I want to show you is its built-in signal generator capability, and for that I'm going to just quickly demonstrate. For that, I have hooked up my oscilloscope to the leads here. Right now we're in the measurement mode. Interestingly, you can see some of the waveforms as it tries to identify the component. Right now let's switch it to signal generation. So you'll see that this is the sine wave at 1 kilohertz. As I mentioned earlier, I did modify the default output. I think the default output was at 10 kilohertz. I found it more useful to be in the 1 kilohertz range here. So the output is at about 3 volts peak to peak, and the waveform is okay, but if you zoom it in, you will see that we do have some quantization effect here, so it's not entirely clean. I believe this one is either a 12-bit or a 10-bit DAC. Can't remember for sure. I think it's a 12-bit DAC, but nevertheless, you do see that quantization noise without the proper filtering here. But it definitely is a feature that you can certainly use it. So the next one I want to show you is, if you tap this, you can cycle through different waveforms. And this again is noise at 100 kilohertz. And the next one is I custom the output for the arbitrary waveform generation to be a staircase. I think that's very useful. As you can see that we have a 200 hertz staircase signal that I found it useful in some situations. So that's really the custom output, and also you have this pulse at 1 kilohertz. Again, the default is at a much higher frequency, and I found it useful to lower the default output, so the waveform here has less distortion. Now the conclusion. I really liked how fast the DT71 does its measurements, although it does not have the same resolution other SMD tweezers typically have. I think the convenience factor is the key selling point given the price tag. You can always use your more capable multimeter to verify the results if you do need that level of precision. Anyway, I hope you enjoyed the video. Please remember to give it a big thumbs up and remember to subscribe to this channel. I will catch up with you next time.